Section 1. Introduction. Introduction. In today's digital age, language models have grown in importance and versatility, finding wide application in numerous language technologies that interact with users directly. This includes search and summarization, conversational interfaces, and collaborative writing, to name a few. Typically, these models tackle downstream tasks using a method known as prompting. What this means is, they are given relevant task specifications and data, formatted as a textual context, and their job is to produce a completed text. These input contexts can be rather extensive, especially when the language models deal with long documents, like scientific or legal ones, conversation histories, or additional information from external sources, for instance, search engine documents or database query results. Successfully managing these use cases necessitates language models that can handle long sequences. However, most language models are built on a framework known as transformers, which do not scale efficiently with long sequences because the complexity of their self-attention mechanism increases quadratically with the length of the input sequence. Consequently, language models are usually trained with relatively small context windows. Recent advancements in hardware, like faster GPUs with more memory, and algorithms have led to the creation of language models capable of handling larger context windows. Yet, it's still unclear how these extended context language models utilize their input contexts to perform downstream tasks. We decided to empirically investigate this question by conducting controlled experiments with a variety of state-of-the-art open and closed language models in environments that require accessing and using information within an input context. Our first experiment was with multi-document question answering, a task which requires models to analyze multiple provided documents, find pertinent information, and use it to answer a given question. We manipulated the input context size and the position of the relevant information within the input context to observe their effects on model performance. For example, we could increase the input context length by adding more documents, and adjust the position of relevant information within the context by altering the document order in the input context. Our observations led us to a distinctive U-shaped performance curve. The performance of the language models was highest when relevant information was at the very start or end of the input context. Conversely, performance significantly degraded when models needed to access and use information located in the middle of their input context. We also noticed that model performance gradually declined with longer contexts, and that extended context models did not necessarily outperform at utilizing their input context. We posed the question: to what extent can language models retrieve information from their input contexts? To explore this, we conducted a synthetic key value retrieval task, a simple experiment designed to test the basic ability to retrieve matching tokens from the input context. In this task, models were given a collection of key value pairs formatted in JSON, and the models had to return the value associated with a specific key. The key value retrieval task also allowed us to make controlled changes to the input context length and the position of relevant information. Just like in the multi-document question answering task, we observed a similar U-shaped performance curve. In order to understand why language models struggle to access and use information in the middle of their input contexts, we initiated investigations into factors such as model architecture, query-aware contextualization, and fine-tuning instructions. We found that some models were relatively robust to changes in the position of relevant information within their input context, but they also showed a U-shaped curve when evaluated on sequences longer than those seen during training. Lastly, we performed a case study with retriever-reader models on open domain question answering to understand the trade-off between adding more information to an input context and increasing the amount of content that the model must reason over. The results indicated that models failed to effectively use additional retrieved documents. Using more than 20 retrieved documents only marginally improves performance. Through our study, we gained a better understanding of how language models use their input context, and developed new evaluation protocols for future long context models. We believe our findings will stimulate further research on improving the way language models utilize their input context. We are making our code and evaluation data available for this purpose. Section summary. Language models are widely used in various language technologies, but their ability to handle long sequences of input context is still unclear. In this study, we experiment with different language models and observe a U-shaped performance curve when varying the position of relevant information within the input context. We also find that models struggle to retrieve and use information in the middle of their input context, indicating the need for further investigation and improvement in how language models utilize their input context. Section 2. Language models. We're focusing on language models, which are essentially functions that receive a textual input and generate a textual output. The most popular type of language model used today is the transformer. Transformers process input text through a mechanism called self-attention, but they hit a snag when it comes to processing very long sequences. That's because the time and memory required by self-attention grow quadratically with the length of the input. As such, these language models are usually pre-trained with a modest amount of prior context, referred to as the context window. This limitation directly caps the maximum length of their input contexts. However, this scenario is changing with the recent progress in hardware like faster GPUs and more memory, as well as improvements in algorithms like flash attention. This progress has led to a quick expansion in the maximum context length that a language model can handle. OpenAI's GPT-4 model, introduced in March 2023, can manage a context window of up to 32,000 tokens. Claude, another model, saw its context window increase from 8,000 to 100,000 tokens by May 2023. In June 2023, OpenAI released an extended context version of its GPT 3.5 Turbo model, where the context length jumped from 4,000 to 16,000 tokens. Additionally, a range of open-source language models that can process long context have also hit the market recently. For instance, the MPT-30B model can handle a maximum context length of 8,000 tokens, while the LONGCHAT-7B can process up to 16,000 tokens. Some recently proposed models can even handle sequences with millions of tokens, which suggests that we might see further dramatic increases in language model maximum context lengths. Shifting gears, our main objective is to delve deeper into how language models utilize their input context. To achieve this, we assess their performance in multi-document question-answering tasks. These tasks require the models to pinpoint relevant information within an input context and use this to answer the question. We specifically manipulate the length of the input context and the position of the relevant information to observe how these alterations affect the model's performance. Section Summary. Language models are functions that take a text input and generate a text output. They are commonly implemented using transformers, which encode input contexts using self-attention. However, the quadratic time and memory complexity of self-attention limits the application of language models to long sequences. Recent advances in hardware and algorithms have led to an increase in the maximum context length of language models, allowing them to process more tokens. In this study, the authors analyze how language models perform on multi-document question-answering tasks by manipulating the length of the input context and the position of relevant information. Section 3.1 Experimental Setup. In this section, we'll be outlining our experimental setup. We're setting up a task that simulates the process used by many commercial search and question-answering applications, like Bing Chat. To explain this, we'll first introduce you to our two main elements, which are I, a question that needs to be answered, and K, number of documents, which could be passages from resources like Wikipedia. Among these documents, exactly one has the answer to the question, and the remaining K1 documents are there to distract and don't contain the answer. The task is for the model to identify the document that holds the answer among all the given documents and use it to answer the question. We have demonstrated this process with an example in the figure. The data for our task comes from the Natural Questions benchmark. It is a collection of real-life queries made on the Google search engine and answers that are human annotated and derived from Wikipedia. To narrow our focus, we're using queries from Natural Questions Open. This is an open domain question answering benchmark, also derived from Natural Questions. We use Wikipedia passages, limited to about 100 words, as the input documents for our task. For each query, we need one document with the answer and K1 documents that do not have the answer. The document with the answer is obtained from the relevant Wikipedia paragraph given in the Natural Questions annotations. To collect K1 documents that don't have the answer, we use the Contriever retrieval system. This system brings us the K1 Wikipedia passages most related to the question, and importantly, these passages don't contain any of the answers annotated in Natural Questions. Please note that due to some ambiguities in Natural Questions Open, a few distractor documents might seem like they contain a reasonable answer. To deal with this, we also run tests on a subset of straightforward questions and found similar results and conclusions. You can refer to the appendix for more details on this. As for the input context, the distractor documents are presented in decreasing order of relevance. While it might seem like a trend to present search results in ranked order, we've also experimented with a random ordering of the K1 distractor documents. The results were not significantly different and the same trends were observed. To assess the performance of our model, we primarily use accuracy as our evaluation metric. It is determined by checking whether any of the correct answers, taken from the Natural Questions annotations, are present in the model's predicted output. We also manipulate the input context length in this task by changing the number of retrieved documents that do not have the answer. Additionally, To modify the position of relevant information within the input context, we alter the order of the documents, which in turn changes the position of the document that contains the answer. Section summary. In our experimental setup, we simulate a multi-document question answering task similar to commercial search and question answering applications. We provide the model with a question and a set of documents, where one document contains the answer and the rest are distractors. We use data from the Natural Questions benchmark, which includes queries and answers from Wikipedia, and we retrieve relevant documents using the Contextualization retrieval system. The evaluation metric is accuracy, measuring whether the predicted output includes any correct answers. We also vary the number and order of documents to test the model's performance. Section 3.2 Models. In this section, we're taking a closer look at a variety of open and closed models, some of the most cutting-edge ones around, to be precise. Our approach for producing results involves a method known as greedy decoding, and we leave the door open for other decoding techniques to be explored in future research. Let's first talk about our experiment setup. We use a standard collection of prompts with each model we test, as shown in the accompanying figure. Starting with open models, our experimental lineup includes the MPT-30B Instruct, which can handle up to 8,192 tokens at once. Initially, this model received training on a whopping 1 trillion tokens, using sequences of 2048 tokens. Later, it underwent additional training using longer sequences, this time of 8,192 tokens, over a dataset of 50 billion tokens. We also put the LONGCHAT13B model to the test. This model, with a context window of 16,384 tokens, is a modification of the Llama 13B, which originally had a context window of 2048 tokens. We managed to expand this using condensed rotary embeddings and fine-tuned it using sequences of 16,384 tokens. Moving on to closed models, we use the OpenAI API to evaluate two versions of GPT 3.5 Turbo, the original one, which has a maximum context length of 4,000 tokens, and an updated version that can handle up to 16,000 tokens. We also assessed the CLAUDE 1.3 and Claude 1.3-100K models, with the help of the Anthropic API. These models can manage context lengths of 8,000 tokens and 100,000 tokens respectively. The GPT-4 model from OpenAI was also assessed on a subset of multi-document question answering experiments, and we found that its performance was in line with the other models, albeit a bit superior. Running a complete evaluation of GPT-4, however, would be rather expensive, potentially costing over $6,000. We then conducted experiments with input contexts that contain 10, 20, or 30 documents, each consisting of 2,700 examples. To get a realistic idea of the performance range, we also tested the models in two special settings, closed book and Oracle. In the closed book setup, models had to answer without any documents to refer to, depending only on their internal memory. Meanwhile, in the Oracle setup, they had access to the exact document containing the answer to the question. Among all, GPT 3.5 Turbo and its 16K variant delivered the highest performance in both these settings, with 55% in the closed book scenario and 88% in the Oracle scenario. More detailed results can be found in the appendix. Section summary. In this section, the authors analyze various open and closed models for multi-document question answering. They experiment with models like MPT-30B Instruct, LONGCHAT13B, GPT 3.5 Turbo, GPT 3.5 Turbo, 16K, Claude 1.3, Claude -1.3-100K, and GPT-4. They evaluate the performance of these models in different settings, such as closed book and Oracle, and discuss the results. Section. Model performance is highest when relevant information occurs at the beginning or end of its input context. Our models are most effective when key information is either at the start or end of their input context. When we shift the location of this key information, there's a noticeable U-shaped curve in the model's performance. This means that the models are most adept at identifying and using crucial information if it's located at the very beginning or the end of their context. However, when the models have to rely on information from the middle of their input context, their performance tends to decline. An example to illustrate this would be GPT 3.5 Turbo's performance in multi-document question answering tasks. It can experience a drop in performance by more than 20% when it needs to find information located in the middle of its context. In certain scenarios, when dealing with 20 or 30 documents, the performance can be even lower than without any input documents, what we term as closed book performance, with a low of 56.1%. These findings tell us that our current models are not yet fully capable of effectively reasoning over their entire context window. when they need to perform specific tasks. Instead, they find it much easier to retrieve and utilize information that's located at the start or the end of their context. As the length of input context grows, we see a significant drop in the model's performance. This decrease is observed in different tasks, showing that our models have difficulty in retrieving and using relevant information from lengthy input contexts. This trend is even more pronounced when we compare regular models with their extended context versions. Consider, for instance, GPT 3.5 Turbo's lowest performance score in a 20-document setting of 52.9%, which happens when the document containing the answer is placed in the middle of the input, 10th out of 20 documents. When the context comprises 30 documents, it's too long for GPT 3.5 Turbo. Even when we use its extended context counterpart, GPT 3.5 Turbo, 16K, we still see a decrease in performance to 49.5% when the relevant document is positioned at the middle, 10th out of 30 documents. While extended context models can handle larger input contexts, they don't necessarily excel at reasoning over the information within these lengthy contexts. Our findings also suggest that extended context models aren't always superior at utilizing input context. In situations where the input context can fit within the context window of both the regular model and its extended context counterpart, their performances are nearly the same. For instance, the results for GPT 3.5 Turbo and GPT 3.5 Turbo, 16K, almost overlay each other. This indicates that just having a longer maximum context window does not automatically make a model better at using this extended context. Section summary. The performance of models is highest when relevant information is located at the beginning or end of the input context, showing a U-shaped curve. Models struggle to reason over long input contexts and have difficulty retrieving and using relevant information within the middle. Even with extended context models, performance does not necessarily improve, indicating that longer context windows do not guarantee better utilization of the extended context. Section 4. How well can language models retrieve from input contexts? In this fourth section, we dive into the question: how proficient are language models at extracting information from their input data? We've noticed that they often struggle to source and apply information from the middle of their input when tasked with answering questions based on multiple documents. Therefore, we're keen to explore how well they can simply pull out data from these contexts. To investigate this, we created a simulated task centered around key-value retrieval. This allows us to specifically examine the fundamental ability of these models to identify and extract relevant information from their given inputs. Here's how we set up our experiment. For our key-value retrieval task, we provided two types of inputs. The first is a string-converted JSON object which contains k unique key-value pairs, all of which are unique and have been generated randomly. The second input is a specific key within that JSON object. The challenge is to return the value linked to that chosen key. In every JSON object, there's one key value pair of interest. That's the value that needs to be pulled out. The rest of the key value pairs, or K1 of them, are essentially there to distract the model. To illustrate how this works, we've included an example input context and the output we'd expect from it in a diagram. We've used accuracy as our yardstick in this experiment, assessing whether the right value is included in the model's output. We designed our key value retrieval task to act as a simple testing ground for the model's basic retrieval skills. Our task echoes the objectives of previous tasks like the little retrieval test and the closely related fine-grained line retrieval task. However, we've aimed to distill and simplify it by removing as much linguistic semantics as possible, and instead used randomly generated values. We did this because we thought that linguistic features could be a confounding factor. For instance, different transformer language models might react differently to varying linguistic features within their input data. In this task, we can adjust the length of the input context by changing the number of key value pairs in the JSON object, either by adding or removing random keys. This changes the number of distractor key value pairs. We can also modify the position of the important information within the input context by changing the location of the key that needs to be retrieved within the JSON object. Section summary. In this section, the authors investigate the ability of language models to retrieve relevant information from their input contexts. They conduct a synthetic key-value retrieval task where the goal is to retrieve the value associated with a specified key from a string-serialized JSON object. The task is designed to isolate the basic ability of matching and retrieving relevant tokens from the input context, without the influence of natural language semantics. Section 4.2 Results and Discussion. In Section 4.2 of the paper, we explore key-value retrieval performance using different input contexts made up of 75, 140, and 300 key value pairs, with 500 examples for each. The experiments utilize the same models as the multi-document question answering tests, and although the synthetic key-value retrieval task only demands an exact match within the input context, not all models demonstrate high performance. Two models in particular, Claude 1.3 and Claude -1.3-100K, perform nearly perfectly across all evaluated input context lengths. However, other models struggle, especially when retrieving keys from 140 or more key-value pairs. The results from the key-value retrieval task follow similar trends to the results from the multi-document question answering task, barring models with perfect performance on the key-value retrieval task. We notice a U-shaped performance curve. The model performance is at its weakest when trying to access key-value pairs located in the middle of their input context. Moreover, model performance generally decreases with longer input contexts. One model, LONGCHAT13B, 16K, is a noteworthy exception in the 140 key value setting. It tends to generate code to retrieve the key when the relevant information is at the start of the input context, rather than outputting the value itself. In Section 5, we discuss why language models may struggle to utilize their entire input context. We observed that language model performance diminishes significantly when they have to access relevant information in the middle of long input contexts. To understand why, we conducted preliminary investigations into the role of model architecture, for instance, the differences between decoder-only and encoder-decoder models, the influence of query-aware contextualization, and the impact of instruction fine-tuning. In Section 5.1, we discuss the effect of model architecture. The models evaluated are all decoder-only models. They can only attend to previous tokens at each time step. To understand the potential effects of model architecture on how language models use context, we compared decoder-only and encoder-decoder language models. Our experiment featured two models, Flan T5XXL and Flan UL2. Flan T5XXL is trained with sequences of 512 tokens for both the encoder and the decoder. Flan UL2 begins training with sequences of 512 tokens for both the encoder and decoder, then continues with an additional 100K steps of pre-training with 1024 tokens for both encoder and decoder. It then undergoes instruction tuning with sequences of 2048 tokens for the encoder and 512 tokens for the decoder. However, as these models use relative positional embeddings, they theoretically can extend beyond these maximum context lengths. We found that both models performed well with sequences of 8K tokens. We compared the performance of decoder-only and encoder-decoder models, using Flan UL2 as an example. When tested on sequences within its 2048 training time context window, its performance remained relatively stable despite changes in the position of relevant information within the input context. But, when tested with sequences longer than 2048 tokens, Flan UL2 performance started to wane when the relevant information was positioned in the middle. Flan T5XXL exhibited a similar trend, with longer input contexts leading to a significant performance drop when placing relevant information in the middle of the input context. We speculate that encoder-decoder models might be more effective at utilizing their context windows due to their bidirectional encoder. This allows them to process each document considering future documents, which could potentially enhance the estimation of relative importance between documents. Section Summary. The Results and Discussion section presents the performance of different models on a key-value retrieval task. Some models perform well on shorter input contexts, but struggle with longer contexts, especially when retrieving keys from 140 or more key-value pairs. The study also investigates the effect of model architecture, comparing decoder-only and encoder-decoder models, and finds that encoder-decoder models may make better use of their context windows, potentially enhancing relative importance estimation between documents. Section 5.2 Effect of Query-Aware Contextualization. 5.2 The Influence of Query-Aware Contextualization. In our experiments outlined in previous sections, we place the query, which refers to the question we're trying to answer or the key we're seeking, after the data that we're analyzing, such as documents or key-value pairs. This setup causes some limitations in decoder-only models, as they can't take into account the query tokens when processing the data, given that the query appears only at the end of the prompt and these models can only consider preceding tokens at each step. However, encoder-decoder models, which use a bidirectional encoder to comprehend input contexts, appear to be less sensitive to changes in the placement of crucial information in their input context. So, could we also enhance the functionality of decoder-only models by situating the query both before and after the data, allowing them to be more aware of the context of documents or key-value pairs? We discovered that this query-aware contextualization significantly boosts performance in key-value retrieval tasks. For instance, the model GPT 3.5 Turbo, 16K, which incorporates query-aware contextualization, scored a perfect performance when tested with 300 key value pairs. Without this contextualization, however, its performance dropped to a mere 45.6% in the same setup. Meanwhile, query-aware contextualization has minimal effect on multi-document question answering tasks. It tends to enhance performance when the relevant information is located at the very beginning of the input context but slightly weakens performance in other situations. 5.3 The role of instruction tuning. All the models that we assessed in our experiments have been instruction tuned. This means they underwent additional fine-tuning on a dataset of instructions and responses after their initial pre-training. In the instruction tuning dataset, the task specification or instruction is typically placed at the beginning of the input context. This might cause instruction-tuned language models to give more importance to the start of the input context. To better understand the potential effects of instruction tuning, we compared the performance of the model MPT30B Instruct against its base model, MPT30B, in multi-document question answering tasks. Both models displayed a U-shaped performance curve, indicating their performance is highest when relevant information is at the start or end of the context. While the overall performance of MPT30B Instruct is consistently higher than MPT30B, their performance trends are quite similar. This aligns with previous findings, which observed that language models have a bias towards recent tokens, that is, those at the end of the input context. Although the benefit from long-range information is generally minimal in the context of next word prediction, our results suggest that language models can use this information effectively when prompted with instruction-formatted data. We think that language models learn to use these contexts from similarly formatted data that may occur in web text seen during pre-training, like questions and answers on Stack Overflow. Section summary. The authors conducted experiments to investigate the effect of query-aware contextualization on the performance of language models. They found that placing the query before and after the data significantly improved key-value retrieval tasks, but had minimal impact on multi-document question answering tasks. Additionally, they compared the performance of instruction-tuned models with their base models and observed that both exhibited a U-shaped performance curve, with the highest performance when relevant information occurred at the beginning or end of the context. These findings suggest that language models can effectively use longer-range information when prompted with instruction-formatted data. Section 6 is more context is always better? A case study with Open Domain QA. We're questioning whether having more context always equates to better results. Here's the thing, in real-world situations, increasing the input context length is a double-edged sword. It could enhance the performance of our language model tuned to a specific task by providing it with additional data, but it also adds to the volume of information the model needs to process. Suppose we have a language model capable of handling 16,000 tokens. Does it actually help to feed it the full 16,000 tokens worth of context? The answer is not universal, as it greatly depends on the particular task at hand, the value added by the extra context, and the model's capacity to utilize lengthy input contexts efficiently. To better grasp this balance, we've done a case study using open domain question answering on Natural Questions Open. Our approach involved a standard retriever-reader setup. Here's how it works. A retrieval system called Contreaver, which we fine-tuned using MS Marco, takes a query from Natural Questions Open and pulls out a specific number, say, K, of related documents from Wikipedia. We then feed these documents into the language model as part of the input. To gauge the performance of this setup, we assess the retriever's ability to recall information and the reader's accuracy, meaning whether any of the originally annotated answers show up in the predicted output. We did this by altering the number of documents the retriever pulled in each time. We focused our experiment on a subset of Natural Questions Open where the long answer is a paragraph instead of a table or list. From the results, we noticed an interesting pattern. The reader model's performance plateaus much sooner than the retriever's. This suggests that the reader models aren't really taking full advantage of the extra context. When we had the retriever pull in more than 20 documents, we saw only a slight improvement in the reader's performance, around 1.5% for GPT 3.5 Turbo and about 1% for Claude. However, this increment came with the downside of substantially lengthening the input context, which subsequently increases the time taken and the cost. Adding to this, we noticed that the models are better at extracting and utilizing information from the beginning or end of the input contexts. With these findings in mind, we believe that improving the way language models use retrieved context may involve effectively re-ranking the documents, by bringing the most relevant ones closer to the start of the input context, or truncating the ranked list, by returning fewer documents when it makes sense to do so. Section summary. In this case study on open domain question answering, the researchers investigate the trade-off between providing more input context to a language model and its impact on downstream task performance. They find that while increasing the context length improves retriever performance, reader models do not effectively utilize the extra context. Increasing the number of retrieved documents only marginally improves reader performance, suggesting that re-ranking or truncating the list of retrieved documents may be promising approaches to enhance how language model-based readers utilize context. Section 7 Related Work ***7 Related Work ***7.1 Improvements to long context language models Numerous studies have strived to design high-performance language models that can handle extended context lengths without relying on the costly scaling of transformers. These efforts have often resulted in variants of the transformer model, where the focus is on refining the attention mechanism. Some of the changes include introducing recurrence, optimizing attention by splitting it into computationally less taxing approximations, or using low-rank approximations. An in-depth review of these approaches can be found elsewhere. Some researchers have developed faster exact attention methods using a specially designed input-output-aware CUDA kernel. Other work has tried to completely eliminate the use of attention to remove the quadratic complexity with respect to sequence length, frequently using convolution and/or linear recurrent neural networks. Examples of this approach can be seen in models like RWKV, S4, and Hyena. Many researchers use perplexity scores on a varied web corpus to estimate the model's capacity to handle long contexts. Our work suggests that accurately accessing specific knowledge within long contexts may present an additional challenge. 7.2 Context use in language models Early research showed that smaller LSTM language models tend to use longer-term context in increasingly broad strokes. Similar findings were reported for dialogue models. Some researchers were among the first to show the potential of merging context from an information retrieval system with a pre-trained language model for unsupervised question answering. It was found that a variety of operations that obliterated information had only minor effects on the predictions made by transformer language models. It was also observed that in moderately sized transformer language models, the generation of long context neural content often breaks down because the models struggle to adequately condition on the long context. Investigations into long context models revealed that extended contexts only improved the prediction of a few tokens. This empirical finding aligns with the theoretical framework that posits that sequence distributions with limited mutual information inevitably lead to only a minor average predictive advantage from increasingly extended contexts. 7.3 The serial position effect *The U-shaped curve observed in this study is related to a concept in psychology known as the serial position effect. This effect explains the tendency of humans, when asked to recall elements from a list freely, to best remember the first and last elements of the list. This phenomenon is crucial in understanding how humans develop short and long-term memory. The presence of a serial position-like effect in long-context language models might be surprising, considering that the self-attention mechanisms underlying transformer long-context language models are theoretically equally capable of retrieving any token from their contexts. Section summary. In related work, there have been various approaches to designing language models with cheaper scaling than transformers for long context processing, such as attention modifications, low-rank approximations, and convolutional or linear RNNs. Previous studies have shown that small LSTM language models and dialogue models make coarse use of longer-term context, while combining context from an information retrieval system with pre-trained language models has shown potential for unsupervised question answering. Additionally, it has been found that longer contexts only improve the prediction of a few tokens, which aligns with the theory that sequence distributions with bounded mutual information have limited benefits from longer context. Surprisingly, the observed U-shaped curve in this work, similar to the serial position effect in psychology, suggests that humans tend to remember the first and last elements of a list, even though transformer language models can technically retrieve any token from their contexts.